Hi everyone. In this video we're going to continue on with chapter 11, which is about inference for categorical variables, and we're going to look at an example where we have a contingency table and we're testing to see if the two variables are independent of each other. Okay? And so we have a simple table here that was just completely made up and taken from somewhere, but that somewhere was completely made up. Okay, the table really doesn't matter that much, but we've got two variables which I'll call gender and handedness. And so I'm supposing that, or the sort of experiment that we're in is seeing if there is some relationship between the sex of a person and whether or not they'd be right or left-handed. Right? So we always are going to start off with the null and alternative hypothesis here. There's not really a parameter of interest, as I usually start up by doing. Really, the parameter of interest is the whole table, or the table as a whole. And so the hypotheses are that gender and handedness are independent. That's the null hypothesis. That's what we're going to go with until we can prove otherwise. And the alternative hypothesis is that gender and handedness are dependent. Remember, and something that's nice about the hypotheses about at least a chi-square test of independence, which is what we're doing right now, is that these hypotheses never change. The two variables that we're looking at, they'll change, but the rest of it is not going to change, and you write it in sort of words instead of symbols. You can write it in symbols, it's just sort of foreign to us and what we've learned so far, and so that's why I put it in words. The significance level will set to be alpha equal to 0.05, just because that's usually the default. And then the assumptions are that both variables are categorical, the data was randomly taken, okay, or the people who were interviewed were selected randomly, and the last one, which is important, is that all expected cell counts are at least 5. And so we talked about those a little bit last time, but it'll be maybe more helpful to see it in practice this time. So both variables are categorical. That's a check because I have two categories for each variable. Of course, you could say there really should be probably more than 2 for the rows, and maybe I need to put in sort of ambidextrous into handedness too, but we will discuss the poor design of the study, just that there was a table. Okay. So anyway, we'll also assume that the data was taken randomly, because why not? And lastly, all expected cell counts are at least 5. Well, we can't see that right now. We have to run the test, right? So we'll wait and see about that. So in order to do this test, you're going to have to use Minitab. You can do this by hand, but it's really tedious and it's not worth our time to do the tedious calculations. So we're going to do it with Minitab, and here's the Minitab output. So you see on the left, it shows you the contingency table, and it also has all the cell counts in it. And so if you'll see, it has 2 entries per cell. So you'll see 1 and 2, and then the columns are called C1 and C2. I didn't take the time to put actual names there, but you can if you want to. But we see the 40, 40, 15, and 5, so we know with respect to the table up in the right what's going on. And so, also if you hear my dog in the background, I'm sorry. He's not happy. If you look below the counts, you'll see 44, 11, 36, and 9. Those are the expected cell counts. And so if you look down at the bottom, it has a little bit of a legend there. It says cell contents. It has count and then expected count. So the expected counts are 44, 11, 36, and 9. So all cell counts are greater than or equal to 5, and we can proceed without worry that the approximation is off, so to speak. Okay, so everything's good with the assumptions there. And then if we look over on the right, you've got two different tests, Pearson and then something called the likelihood ratio. We won't worry about the likelihood ratio now, but certainly you can come and talk to me about if you're interested in the difference between the two, because I know quite a lot about this specific topic more than others because it was my research area. And so I could talk about the differences between the two and the different formulas. But anyway, I digress. What we're interested in is the Pearson number, which is a 4.04. So that is our test statistic. And the p-value is 0.044. So it's a right-tailed p-value, of course, because this is always a right-tailed test. And so p-value is 0.044 because, or since the p-value is less than the significance level, really it's because the p-value is less than the significance level, we reject the null hypothesis. And at the 5% significance level, there is enough evidence to conclude that there is an association between gender and handedness. Now, this is one of the cases, if you look at this closely, 40 and 15 versus 40 and 5 is not convincing to me personally that the two are different. So this is a case where I might dispute, not dispute that there is statistical significance, but it doesn't really mean anything practically to me here. Okay, and we can see that in the fact that the p-value we're sort of barely significant. If I chose alpha equal 0.01, I would fail to reject. And so we have a p-value that's close, but not quite, there. So that is an example hypothesis test. Now, let me show you. Let me back out of this for this problem. And so all that we need to do is input the four specific numbers for the contingency table, 40, 15, 40, and 5. And then we can go to stat. And we're working with tables, so we want to go to tables. And then you have a number of different options. You want to go to cross-tabulation and chi-square. Okay, cross-tabulation and chi-square. And I've already done this, so it's here, but let me reset. Reset. It gives you options up here, raw data in categorical variables. We don't want that usually because we've already made the contingency table. This, the raw data, it would first make the contingency table for you and then do the analysis. But we already have it. So summarize data in a two-way table. And so it asks me what columns I want. I want both C1 and C2. And then here it asks for labels of the table, but I haven't put any table labels in my worksheet down here, so I don't click anything for that. And I want it to display, I think, only the counts. I don't want any percentages because I'm not asking you to do any sort of probability things, but we do want to go to chi-square here. And we want it to actually compute a chi-square test. We want the p-value and the different statistics that we want. We want the expected cell counts for our assumptions. Okay, when I click OK, that's good. We could go to other stats here and look at a bunch of different tests that we could talk about. We just don't quite have time, or don't really want to take the time to talk about all of these. Okay, but these are other tests that happen when maybe Pearson's chi-square is not so good for us. Okay, and I'll talk about that in just a second. But all that I want are the columns there. I got my expected counts and my regular counts and the test. So I click OK. And so here in the top, you'll see the table with the regular counts and expected counts. And then once you go down here, chi-square test, here's the Pearson number, the test statistic, and the p-value. Okay, and so that's how you go through again there. So here's a your turn. I give you a small example here with the types of work that people do and the neighborhood that they live in. Right? I want you to do the same thing at the 5% significance level. Am I able to conclude that the neighborhood and occupation type are independent? Okay. Now, the last thing before we go is that these types of tests, Pearson's chi-square test, as many things in statistics, are often misused, or they can be misused. And so here it lays out a number of different times when things are misused. When the expected frequencies are too small, you shouldn't use the chi-square test. There's another test called Fisher's exact test that was in that other stats column in Minitab. Fisher's exact test is for when those expected cell counts are too low. And then there's a whole other host here that happen. Basically, what it's laying out are that one or more of the assumptions are violated. So third one down is that the data don't result from a random sample. And the third one is when you have quantitative variables instead of categorical ones. Okay, and so 1, 3, and 4 are just the basic, like, not looking at the assumptions is when you can misuse it. And then the second one, when separate rows or columns are dependent samples. You have to have sort of independent samples, yeah, for this to work. And also, not on the misuse part, but the chi-square test does other things, or this whole sort of way of thinking about testing not only works for testing independence, but it also tests many other things. So another very popular one is called goodness of fit. There's another test for association. Actually, this is association. Is independence or not? But there are a number of different ones that fit this example, okay, or fit this testing sort of outline. Okay, and so that's the end of chapter 11. And so next time we're going to move on to chapter 14, which is called the ANOVA.